MCQ question number 25. In this question, we have been asked to find an expression for the output y. Now we can see that in this logic circuit, gate number 1, 2, 3 and 4 are being mentioned. So we can say that the output y will be equal to y2 plus y3 ka whole bar, where y2 and y3 are the outputs of gate number 3 and 2 and 3. y2 can further be written as bracket a plus b bracket close dot c whole bar, and y3 can be written as t dot d whole bar. So y, that is our final output of gate 4, can be expressed as bracket a plus b bracket close dot c whole bar dot d dot e whole bar. By De Morgan's theorem, we can express this output y as y equals to bracket open a plus b bracket close dot c plus d dot e. That is, option D will be the correct answer. MCQ question number 28. In this question, we have been given two electric fields E1 and E2, and we have been asked to find which of the following statements is true. Now we can see that all the four statements is related to only one expression, or we can say one question, that is, which of these two electric fields are valid. Now from Maxwell's equation, we can say that curl of E, that is curl of electric field in a static system, is always equal to 0. So we will apply this equation for these two E1 and E2, and we will find which of these two equations or which of these two electric field are valid. Now if we apply curl operation on electric field 1, that is x cap plus y cap, we will find that del cross E1 is equal to 0 x cap minus 0 y cap plus 0 z cap, which is finally equal to 0. So del cross E1 equals to 0. That means the first electric field E1 is a valid electric field. Now if we apply the same operation, curl operation, on electric field second, that is xy square x cap plus y square y cap, we will find that the curl of E2 will come as x cap 0 minus 0 y cap plus 2xy z cap. So the curl of E2 will come as minus 2xy z cap. As we can see that the curl of E2 is not equals to 0, so E2 will not be a valid electric field. So the correct option will be option C, that is, only E1 can represent electrostatic field.
MCQ question number 30. Consider 10 atoms fixed at lattice sides. Each atom can have magnetic moment mu b or minus of mu b in the z direction, and f is the function of magnetic moment mu denote the probability. In this question we have to find out f of 2 mu b divided by f of 0. So the magnetic moment can be 2 mu b if 6 atoms in plus mu b state and 4 atoms in minus mu b state. Then the microstats with respect to the system n1 equals to factorial of 10 divided by 6 factorial 4 factorial, that is equals to 210. And again, for the magnetic moment to be 0, 5 atoms should be in plus mu b state and 5 atoms should be in minus mu b state. Then with respect to this, the number of microstats n2 equals to 10 factorial divided by 5 factorial into 5 factorial, that is equals to 252. So the probability will be proportional to the number of states That's why the function of 2 mu b divided by function of 0 magnetic moment, that is equals to 210 divided by 252, that is equals to 35 divided by 43. Option A is correct.
MSQ question number 36. In this question, we have been given that a common base amplifier is driven by a voltage ES of internal resistance Rs equals to 1 kilo ohm. The load impedance in the circuit is a resistor RL which is equal to 1 kilo ohm. All the H parameters for this particular circuit are given to us, that is HI, HR, HF and HO. HIB, that is input impedance, is given to us as 22 ohms. The reverse transfer characteristics, that is HRB, is given to us as 2.9 into 10 raised to the power minus 4. The forward current transfer ratio, or HFP, is given to us as minus 0.98, and the output admittance, that is HOB, is given to us as 0.50 microampere per volt. Now, we have been asked to calculate the current gain, input resistance, voltage gain and power gain, because these are the four options whose value has been given to us, and we have to find which of these following statements are true. So, first of all, we can directly calculate the current gain from the given parameters. Current gain, which can also be represented as AI, can be calculated by using the formula minus HFB upon bracket HFB into RL plus 1. Now, if we put the given values that is given to us, we will find that the current gain is equal to 0.98. Further, input resistance can be calculated as HIB, that is input impedance, plus a factor which comprises of HRB into AIB into RL. If we put the values given to us, we will find that the input resistance Ri will be equal to 22.28 ohms. The third option that is given to us is voltage gain. So we'll try to check if the voltage gain given to us is correct or not. Voltage gain AV can be calculated with the help of current gain, RL and input resistance. We can use the formula AV equals to AI into RL upon RI. If we put the values calculated by us, we will find that AV, that is voltage gain, is equal to 43.99. Further, we can also calculate the power gain because voltage gain and current gain are already calculated by us. So we can calculate power gain directly by multiplying voltage gain and current gain. That is 43.99 into 0.98, which will be equal to 43.11. Now, from all the values calculated by us, we can now tell that option A, B and D are the only statements which are correct. So the correct options will be option A, B and D. NET question number 51. In this question, we have been asked to calculate the minimum number of NAND gates required to implement an expression A plus AB plus ABC. Now we know that NAND gate is X dot Y is whole bar. So we have to simplify this given expression in the form of dot and bar. If we simplify this expression, Y equals to A plus AB plus ABC, we will get A common, and we can safely write Y equals to A bracket 1 plus B plus BC bracket close. So the final expression that we will get is Y equals to A. Now to implement this expression Y equals to A, we don't need to apply any NAND gates because A will be available to us as input. So the number of NAND gates required will be 0. So the answer to this NED will be 0.